In this video, we're going to combine the techniques from the last two videos to do a more advanced return to libc attack where we also bypass the PI protection. So in our previous return to libc attack, we simply got the base address of the libc library using LDD on our local system, and then we calculate the offsets using readelf and strings. But typically that's not going to be possible. If we were running this against a remote server, we're not going to be able to run local commands on their system until we get a shell. So we need to find a way to leak a libc function so that we can then find a way back to the base, and then find a way to the functions that we're interested in, bearing in mind that every system will have a different version of libc and it'll have different offsets and things like that. We learned in our last video that we can use format string vulnerabilities to leak addresses off of the stack. So that's certainly an option, to leak the libc address, but that's not what we're going to do. We're going to leak the PI address using a format string vulnerability, and then we're going to use a different technique to leak out the libc address. It's not that we can't use the format string vulnerability to leak both addresses, it's just that I want to show a couple of different techniques so that we know that if there's a buffer overflow, we can leak addresses using that, and if PI is enabled, then we know how to use a format string vulnerability to leak the PI address. So let's go and do some basic file checks. So let's see what we have here. We've got a PI server. This is owned by root, and we've got all the same permission settings as we did previously for the flag and for PI server. I'll not go over how to set those. I've done that in plenty of videos now, so you can go back and grab the commands if you're not too sure. Just to mention that we've compiled it this time, so we've got no stack protector, so that's the canaries. But apart from that, we haven't actually specified any other protections. So let's first of all just check the file type. We didn't specify -m32, so it's a 64-bit binary. And notice that this time it actually says PI. It's also not stripped, it's dynamically linked, so all that stuff's the same. Let's have a look with checksec as well. You can see that we've now got NX enabled, which we had previously, but we've also got PI enabled. So we've discussed this protection a little bit a couple of times, and we had a look with Radare to see how binaries look different when PI is enabled or disabled. But let me just bring up an article, so I'm going to go back to this nightmare blog sort of thing, which has a lot of different CTF write-ups and goes through a lot of different types of buffer overflow challenges and binary exploitation challenges in general. So they talk about ASLR here. We saw ASLR. Remember, we had to turn ASLR off. In fact, I probably have to do that as well. Let's just see if we do LDD on the PI server. We do it again, and you see each time I'm doing that, we've got a different base address. So I'm going to turn ASLR off. I've just got a command to do that, but if you want to do that, you can. Well, let me just show actually. Let's grep ASLR off from my bash aliases, just in case you didn't see the previous video. And basically we can take a copy of this command and just echo that 0 to proc sys kernel randomize va space. So I'm going to do that, and now if we do LDD, each time we do that we've got the same base address. There's a good description of this here as to what ASLR is, address space layout randomization. As for PI, position independent executable is another binary mitigation extremely similar to ASLR. It's basically ASLR, but for the actual binaries code and memory regions. So for instance, let's take a look at a binary compiled without PI. And we did this previously, right? So we had all these fixed addresses. Let me zoom in a bit. We had all these fixed addresses, and for example, if you think back to when we did that return to win challenge, we were able to just take a copy of the address and say that's the address we want to overwrite the return address with, because we want to jump to that hacked function. Well, whenever we enable PI, we're not going to see that. We're going to see instead an offset each time. So each time the program loads, it's going to have these same offsets at the end, but this base address isn't going to be predictable. So if we were doing that return to win challenge where we wanted to return to that hacked function, we could get the offset to the function, but we wouldn't actually be able to overwrite the return address with the correct address until we leak that base address. And the way we would do that is try and leak some address in the binary where we know what function it is or what it's pointing to, and then we know what the offset is to that function, so we remove that offset and then we get the base. Just exactly the same as leaking the libc library. We'll show how to do that shortly anyway, just wanted to touch on that as a protection. We've seen what protections are enabled. Let's go and take a look at the source code in Codium. Again, we're typically not going to have access to this, so I've also got this open up in Ghidra as well, because normally you'll just have the binary, so get used to looking at the code in here instead. But what have we got? We've got this main function. We can see we've got this set UID and set GID, which is just to do with making sure that we get full root access when we get a shell or we want to try and print the flag. It's going to call enter name. We've got 64 character buffer here, 64 bytes. It's asking us for a name. It's going to use fget, so it's using a secure function to read this in. You can see that it's actually making sure that the input from our standard input is going to be the size of name, so it's going to be nothing more. And then it's got printf hello and then printf name, which is what we saw in the last video. So even though there's no buffer overflow here, we know that an attacker can control what is sent to printf, and because they haven't specified a format, we can do it for them, which means we can leak addresses off the stack, we can write things to the stack, etc. And that's it. It's going to return from that enter name function where there's no buffer overflow. It's going to say good luck with your return to libc, you'll never bypass my new PI protection or find out where my libc library is. And then it's going to call Vuln. So this is where the buffer overflow is. We've got a 256 byte buffer, and it's using the dangerous gets function this time to read into this buffer without first checking to make sure what we enter is actually going to fit. Nice quick source code review this time. Let's go and take a look at that in Ghidra as well. So we go in here, go into our functions, we've got our main, we could go and start renaming stuff here. I'm not going to do that this time. And I just want to talk through what we're going to do again. We know that we can use the printf to leak some variables off the stack, and we'll look at that very shortly. But let's just say that we didn't have a printf vulnerability, we didn't have PI enabled, we were just doing a buffer overflow, but we wanted to leak out the address of that libc library. You'll remember that we talked about the global offset table and how if you've got a dynamically linked binary, it's going to call out to your libc library, so it's simply going to populate the global offset table with the address to the functions in your libc library. So how could we leak one of these addresses in order to then find our way back to the base address of libc and find our way from there to system and to bin.sh and things like that? Well, if we've got a buffer overflow, and let's say we've got a function in the program like puts, which we do, well, providing PI isn't enabled and we can get access to this puts function which is used, or to printf or something like that, we could simply put out one of these addresses. So we could pop the global offset table address to one of these functions, let's say gets, let's say we pop that into the RDI, and then we overflow the buffer with the return address of puts. So puts is going to then have a look in the RDI and see what am I printing to the screen. It's going to see we want you to print the global offset table address for gets, and that's going to leak the address for us so that we can then find our way back to libc. Now the only thing is it needs to be a function that's already called so that the address has already been populated, or it can be a function that you're actually calling. So let's say puts hasn't been called, we could call puts to print out the global offset table of puts address and it would print out the correct value. So that's the technique to leak the libc library just using a buffer overflow, and we will do that. We'll do that to leak the libc library, but first of all we need to find out what the PI address is, the base address, because we can't call puts until we know where puts is. Let's go over this attack properly. Let's go back to our main function. We're going to call enter name. This is where we're going to leak some values off the stack. So what we want to do is try and find out what index do we have to some kind of function or something in the program that's going to be the same each time, that we can then find our way back to the base of the binary, and then from there we'll know where all of the functions are. So that's what our goal is going to be, to leak out something which we can then use to calculate the PI base. Once we've done that, and we've got to the standard place that we have been in our previous binaries where we know where all the functions are, we can call anything in the program, then we're going to go to the buffer overflow. We're going to go to the buffer overflow, and the first buffer overflow we're going to do, we're going to say we want to print out the global offset table of puts, and we're going to use puts to do that. So we'll pop the global offset table of puts into the RDI register as the first parameter, and then we'll call puts, it'll put it out to the screen, and then we want to return back to the start of this function, or back to the start of main or something, because we need to do another payload, right? We've leaked out the PI base address, and we've used that in order to call puts to leak out the global offset table puts address, but we've not actually taken over the system. So we need to go back to the start of Vuln, or back to the start of main, and then do another buffer overflow, and this time use the libc library that we've leaked to return to system. Hopefully that makes sense. By the way, the global offset table, notice that we have a global offset table and we have this global offset table PLT, the procedure linkage table. I'm going to go through that in a bit more detail in the next video where we talk about overwriting elements in the global offset table, but I'm just trying to kind of simplify things here. We'll just say this is a global offset table and we'll expand on that a bit in the next video. One thing I do want to show, if we open this up with gdb-PwnDbg, So we actually have some options in here. Let's first of all, let's view the functions, and we'll see that we don't have these full addresses this time, we've just got these offsets. So this base address is going to be different each time, but the offsets are going to be the same. So if we can leak out, for example, this Vuln function, all we have to do is subtract this 11D6 from the value that we leak, and we're now back at the base of the binary. And then we can say, if we want to find then enter name, we can just add 1185 to that address, and we're at enter name. So there's some functions in GDB to actually calculate the PIEBASE. You can see here if I try and type PIEBASE, it says the program's not being run. Let's break at main, let's run the program, and then let's ask what the PIEBASE is. And you can see here it's telling us that this is the PIEBASE address. So you could then go and use this to calculate offsets and things like that. I think actually, let me do PIEBASE-H or PIEBASE help. It's been a while since I used this myself. Help PIEBASE calculate. Okay, so it's just fine. Alright. Well, you also have breakrva. Let me have a look at that. So if you just do breakrva, I think that's just done a break at the PIEBASE. But you can give an offset. So if we go back to our code here, let's say we wanted to put a breakpoint here. So we take this offset, it's 11F0, and we'll say breakrva. I don't think we need a star, but let's just see. We don't, okay, without the star. And that's going to set up a breakpoint there, which basically means that each time the program loads, even though it's going to have a different address, it's always going to set up a breakpoint at this offset from the PIEBASE address. And we can go and put this in our PwnTools scripts. Remember, we have the little GDB script that we set up there, so we can go and add PIEBASE if we want to print out the PIEBASE each time we open it with GDB. We can break RVA from whatever functions we're interested in. And it means that we won't need to set up like a breakpoint at main and then go and set up an individual breakpoint each time we run it. It'll just do this for us. Just to mention, by the way, I've mentioned this before, but in GDB, PwnDbg, there's so many options. Just type help if you're not sure where to go. You'll see a lot of different options here, and then say, let's say we need some help with breakpoints. We'll do help breakpoints, and then it's going to give you all individual commands. You can drill down on those as well. Or you can type PwnDbg, and you'll get a list of different commands that we can run from inside here. So you can actually call ROPer from in here. You can call radr as well. You can do quite a lot of stuff. A lot of stuff which I don't know how to do, but let's try and actually overflow the buffer. So let's do our cyclic pattern. I'm actually going to delete the breakpoints. Let's generate our cyclic pattern of, let's say we had a 512 buffer, did we? Or 256. I'm going to do 500 bytes. Take a copy of that. We run it. It's asking for the name. Alright, let's leak something out. We'll do a couple of pointers. You can see here it's printed out these stack addresses. This looks like hex. So you could go ahead and I could do Control and C, unhex, paste that in, and that's actually the pointer string that we put in. Alright, so we'll hit continue. Did it ask for something? Okay, it was actually asking for the buffer overflow there. Okay, let me do that again. Name, alright, this time I'm just going to say anything, and now it's asking for the, oh, I need to copy that cyclic pattern again because I copied the hex value. So now it's asking for our input. This is the buffer overflow. Paste that in. We obviously hit this breakpoint, or not a breakpoint, but it's crashed the program, so we need to go and have a look and see what are the first 4 bytes in the RSP, because that's what would have made it into the RIP. And we'll do cyclic-L, look that up, and we'll see that there's 264 bytes we need to write before we'll be overwriting the return address. And remember, this time we're going to overwrite the return address with, first of all, a ROP chain which is going to call puts to leak out the global offset table puts address, and then go back to the start of the vulnerable function. And then we're going to do another ROP chain to call system bin sh. Okay, let's move on. I'm going to do my best to keep this video under 30 minutes. We're going to do some fuzzing anyway, which we want to do to try and identify those values on the stack. Let's open up this fuzz.py script. Similar to one that I put together previously, where we looped through 100 values in the last video actually, where we printed off the strings off the stack. This time we're using pointers. Remember that when we print a string, it's not actually printing the value on the stack as a string, it's using that address and go into that location and printing whatever's there as a string. So this time we're actually printing the value off the stack because we're trying to get these addresses. And we're doing 100, but there'll be a lot of different values that we can use. It doesn't really matter, we just need to find one that we can use to calculate our way back to the base of the binary. And we'll do that by using GDB. So you can see I've got GDB set up here. We could do our break-RVA. I've just got PIEBASE at the moment. And I'm going to use GDB so that I can then go and have a look to see what the addresses that are leaked are actually pointing to. So let's try. I think I might need to do, let's see, I should have actually kept this. No, let's have a look. Let's have a look at this. Alright, so we're going to do Python Fuzz. First of all, let's just do Python Fuzz. You can see we leak through all these addresses, and that's great, but we need to go and see what they actually point to. Now, you can see that this looks potentially interesting. 5295, we can run that again. 5295, so we want to find an address that stays the same each time, or the offset stays the same at least, and we want one that's obviously part of the binary. So these 7F addresses is generally a good sign that's going to be an external library like our Lib-C functions, which we can go and have a look at. This looks like some hex, so you could go and unhex this and see what kind of characters it's actually showing. But let's try and do this with GDB. Now, the thing that I realized with this script, I took this script from what we did last time where we printed out the strings, but remember that we started the program each time we wanted to get a new string because there's a good chance that it will try to read an invalid memory address and cause the program to crash. But in our last example, we had a printf, it was just looping around trying to take input from us, so we could have just, if we were printing pointers, we could have just not restarted the program after each loop, and we could have gone through and looped each time and printed out, say, 100 or 1,000 values off the stack. This time we can't do that, so if we start this program each time, it's going to open up 100 instances of GDB, as in 100 windows, which is not what I want to do. So what I'm going to do instead is go and run this script again, and we're just going to pick out some interesting addresses. So all of these look like they could be from Lib-C or something. We could be able to find our way back to Lib-C from these 7F addresses. And then we've got all these 55555 addresses, which hopefully we'll be able to use to calculate our way back to the base of the binary. So for example, this one 9, let's go back and update our script and say we want to print, I think it's going to be 9 to 10. I get these indexes confused sometimes. Let's do this with GDB. And you can see it's printed out the address, so we can go and have a look now. If we do X, provide that address, and we've got this libc CSU in it. And we can see our PIEBASE address as well at the top. So we could essentially take our PIEBASE address, let me take a copy of it, and we could take this address here and we'll say X, there's the PIEBASE, and we want to take a copy of this libc CSU in it. Minus, and then we'll see what is the offset. So presumably each time we run the program, if we leak the 9th element off the stack, I think it's the 10th element actually because it started at 0, and then subtract 1295 in hex, then we're going to get back to the base of the binary. Now I think I used 15 in the script, which is fine as well. Let's do 15. 14 to 15, right? Try that again. No, that wasn't it. Okay, but this might be a Lib-C address. Let's take a look at it. Okay. I think because that closed down, it's maybe not going to show it. Let me go back. 15 to 16, was it? I bet you it's going to be 14 to 15. Okay, no, there we go. So I think this is the one that I leaked in the Python script we put together. It's main plus 44. So again, you could take this and you can say we want to subtract the... Sorry, that was the wrong way around. We want to print X and then the address that we just leaked there minus PIEBASE and see, alright, it's 1224. So if we put together an exploit, we're going to say, alright, leak the 15th element off the stack and then subtract 1224 in hex, and you've now got the base of the binary. So if you want to then find your way to another function, all you've got to do is add the offset of that function, and that'll be you there. We're going to take a look at 3 different PwnTools scripts to solve this, and let me just start off with exploit.py. So each one just has a little bit more automation. I'm going to go and comment out some of the stuff so that we can just focus on this one step at a time. Let me comment all of this out. And this should be our PIEBASE, hopefully. Okay, so the usual template. I don't have the find instruction pointer function here because, as I said in one of the previous videos, if the server's running as root, it dumps the core dump as root and then it's not able to read that. It's fine, we're just going to specify this manually as 264. We've got our pop RDI offset, which we don't need just yet, we need that later, but you can grab that from Ghidra or GDB, whatever. I normally use ROPer because it'll just show the ROP gadgets rather than showing everything, and we can provide PyServer. We can search, or we can just list them all and have a look for it, but let's search for pop RDI. We get our gadget, it's at 12AB, which we have there. Because we have the context.binary set, we don't need to worry about putting all these zeros in. It knows we're dealing with a 64-bit address. Again, this is the offset, so we're going to leak. We can't actually use pop RDI until we've leaked that PIEBASE address. And that's what's happening here. So it's going to go to that printf format string vulnerability. It's sending off the 15th element, so it's saying print the 15th element on the stack as a pointer. Just trying to work out what the 16 bits come from. I think that was accidentally pasted in, but it didn't seem to cause any problems with it anyway. But that's fine, let's take that out. So yeah, it's going to print the 15th element off the stack as a pointer, and we know that that is main plus 44. We just went and identified that manually, so we can subtract then the 1224 that we just saw in GDB, and then we have the base address of the binary. Now, what I typically do then is update the elf.address. Remember, we've set our binary up here, and if you do that, it means that later on in the program we'll be able to just call functions directly from the elf, because we don't need to specify, we don't need to hard code the addresses because we've updated the base of the binary. And we can do the same thing with Lib-C as well. So let's just first of all take a look at that. Python exploit. It's going to run through, it leaks out the address, and then it shows us the PIEBASE address. It looks like it's calculated it all correctly, so we can run it a couple of times. We're actually getting the same base address anyway, but it's fine. Let's go back. And then once we've done that, then we're going to update our pop RDI. So pop RDI is going to be that offset that we found with ROPer plus the base address of the binary. And we're going to go and do our buffer overflow. So let me uncomment this. Let's uncomment all of this, and we'll talk through it. So we've leaked our address, our PIEBASE address. Again, we could overflow the buffer and go back to that printf vulnerability and then just leak another address. But in our case, we're actually going to use our first payload to overflow the buffer with the pop RDI gadget, which is going to pop the elf.globaloffsettable.puts address into the RDI register. And then we're going to use elf.plt.puts to actually print out the address of the global offset table puts to the screen. And that's us leaking a Lib-C function address. We're then going to return back to the Vuln function because we want to do another buffer overflow, and this time actually get system. So we send that off. We just have to receive a couple of lines in order to continue, and then we're going to retrieve that global offset table puts address, which is going to be printed out to the screen. And then we're going to go and calculate our Lib-C base. We're going to calculate our way to these other addresses. You can see I've got these in manually, but I'll show how with another script how we can kind of do that a bit differently as well. Then we're just going to send off our other payload. So at this offset, which is 264, our padding, we're going to pop the bin.sh string into the RDI register, and then we're going to call system. Send that off, and that should be us getting a shell. So what I'm going to do, let's comment out this bit for now. I'm going to go back and let's just go and verify how we can confirm those addresses are correct, because quite often they won't be. Maybe you've leaked an address improperly, or you're not getting it out properly with regex. If we do Python exploit GDB, we can get this GDB window up and go and actually compare what we have here. So you can see we've leaked out these addresses. We've got our global offset table puts address. We might go and do X. I need to do this interrupt again, do I? Okay. Interrupt, Control and C, and then we'll do that again. So here's our puts address, which is great. So what we could do is take that address and say, if we subtract this from our Lib-C, if we subtract the offset, there's our global offset table puts address. I'm going to go back and let's go back to our code. Here we've got this offset, which again, I can show the command that we use to find that on the local system. We do minus, we get this address, and then we could go and say, okay, what is that? Okay, that doesn't actually show very well, but that's the the base of our libc library, we've got our, you can see it's the same address here anyway, it calculated the same address. We've got our system address, so we'll go and confirm that as well, libc.system. And we've got our bin.sh string, which is, if we want to print as hex, we can do x over s bin.sh. So everything's lining up properly as we would expect it to. Let's go back one more time, uncomment this last bit to send off the shell. Let's run it without GDB. And we get interactive mode. We can now do who am I, we're root, so we can cat out the flag.txt. And we can go and have a look through what's happened here. This has all been sent off and received. Because we've got the debug mode set, we can actually see what's sent, what comes back. So this was our leaked address, as you can see. And then we send off another buffer overflow to get the shell, and then we switch to the interactive prompt. Now, one thing you might be thinking is, I've been mentioning running these exploits against a remote server, and we won't know what these offsets are for the libc library that they're using. Well, as long as we get things working locally, in this case we were able to find our libc base locally, we were able to leak the global offset table puts address locally. What we would do here is run the same exploit against the remote server and have a look at what address is leaked. So let me actually do that one more time. Let's do Python exploit. So we've got, for example, our puts address here. Let's say I run this against a remote server. It prints out the address, and I know it's puts, but I don't know what libc library they're using. Well, you can go to the libc database, which is Blukat, libc.blukat.me, and we can basically go and, let me add the address in here, and then you'll just say this is puts, use find, and that's going to tell us what possible libc libraries this could be. And then you can go through, you can either go through all of them and just go and try them out, so you go and try and update your offsets, or you can actually download these libraries, and then locally you could set your script up to go and loop through them and try them all against the remote server. Obviously you can get an idea based on the architecture and things like that as well, but that's how you would typically do that against the remote server if you don't know what version of libc is running. Sometimes you'll do a CTF challenge and they'll actually provide you with the local libc library that they have on the system, so you can get everything working locally, and then it'll just work against the remote server as well. Alright, this video is already getting quite long. Let me quickly jump over to our other scripts. Let's see what we've got. So we've got an auto pwn script. Let me open that up. I can't actually remember exactly what was different in this one. Okay, in this one we have loaded our libc library. You can see here this is the address of the local libc. We've loaded it as an elf, and that means that whenever we get down to our return to libc attack, this is the only bit that's different. We're doing all this stuff up here the same, but when we get down here, whenever we leak out the libc address, we're actually going to update the libc binary base address, and that means that whenever we get down to our payload, we can simply call libc.symbols.system or libc.functions.system, and we can also search the libc library for the bin.sh string. So Python autopwn, we run that, we've got a shell, who am I, we're root, so that's all good. The good thing about this is that if I run this exploit against a remote server and I can find out what version of libc they're using, or they provide it, all I have to do is just update this to their libc library. So let's say we download that libc library off libc database. Let's say there's 4 possibilities. I could just loop through all 4 and simply just run the script. I don't need to change any of the code apart from this. No, you won't need to change that pop RDI offset, so you don't need to change anything, and you'll just try each of the libraries until one of them gets you a shell. Okay, and let's have a look at the final one, so ROPstar. And this one's just automating things to the max. We've got our libc library as an elf. We're still using this to find our offset. We could actually search for that as well, but that's fine. And you can see down here then we create a ROP object of the elf, and we just call rop.puts and pass in the parameter elf.got.puts. That's going to put that out to the screen. Let's print this out as well. And then it's going to call rop.vuln again because we want to send off another payload. We leak the address, we update our libc library, so the libc base address is now equal to the got puts that we leaked minus the offset of libc.symbols.puts in our libc library. And then we create another ROP object using the libc library where we simply call ROP.system and search for the bin.sh string. So again, we can do pretty print rop.dump, and If we run this, we'll be able to actually see how they're putting together the payload. So let's first of all just confirm we are root, which we are. We scroll up and we'll see, alright, the first payload, it simply found the address of the PopRDI gadget. Oh, so we didn't need that at all, sorry, we could take this completely out of there. And it's found the PopRDI gadget, it's put the got.puts address into the RDI. It's called puts to put that out to the screen, and then it's called vuln. And these are just the addresses of those functions and gadgets. And then for Lib-C, it's called PopRDI, it's put the address of bin.sh into the RDI, and then it's called system. And that's got us the shell. And that's going to wrap it up for this video. I'm not going to do this in 32-bit, I'll leave that for you to do yourself. There's not really going to be too many differences anyway in terms of, well, apart from the fact that we don't use the RDI register and stuff, and the address lengths will be a bit different. So next time we'll be looking at how we can overwrite elements of the global offset table using a printf format vulnerability. So let's say there is no buffer overflow at all. How can we still get a shell just only using the printf format string vulnerability? And I hope you've enjoyed this video. If you have any questions or comments, leave them down below. Thanks.